If you follow science news at all, you probably know that astronomers are forever discovering things. It seems like every week they announce the discovery of something new, a giant star, or planets around some other star, or some giant black hole, or even a whole galaxy that nobody has ever seen before. But the most amazing thing about all of these discoveries is this. For every new thing that astronomers discover through their telescopes, there's 5 times as much stuff out there that they can't see at all. It's called dark matter, and no one knows exactly what it is. Now, that might seem incredible, right? Ordinarily, insisting that you're surrounded by vast amounts of invisible stuff that no one can see is a great way to get yourself locked up. So how can this be science? What sort of bizarre process would lead astronomers to conclude that we're surrounded by all this invisible dark matter? The answer is surprisingly mundane. Astronomers are led to the idea of dark matter through the same process that you use when playing cards. Now, I don't mean that this whole dark matter thing is a bluff or that astronomers got lucky. I'm talking about the reasoning process that a good card player uses to figure out who's holding what in a game like bridge. Bridge is one of the most popular card games in the world, and what sets it apart from other games is the bidding process that opens the game. The players take turns going around the table offering a number and a suit. 2 hearts, 3 diamonds, 4 spades, and so on. The suit is what they would like to be trump. The number is how many tricks they think they can take together with their partner who's seated across the table. Now, if you're bidding on how many tricks you can take together with another person, it would be really helpful to know what cards they're holding. But you're not allowed to look at your partner's hand, and you're not allowed to directly ask what they have. Instead, you have to deduce what they're holding from the bidding process itself. This is possible through a set of conventions that have grown up around the game, which are particular bids that you use to signal your partner what you're holding. A good bridge player with good knowledge of the conventions will enter a hand knowing almost exactly who has what cards, just from the bids that they've made. Astronomy is a lot like bridge. Astronomers want to figure out what's going on at a distant point in the universe, but as much as they might like to, they can't actually go there to investigate in person. Instead, they have to deduce what's happening through the light that reaches their telescopes here on Earth. Astronomers are a little better off than bridge players because they have 2 questions they can ask. How much light comes from a distant object, and what color is the light that comes from a distant object? Using those, together with a set of conventions, in this case the laws of physics, allows them to extract an incredible amount of information from those 2 questions. Because we understand the physics of how stars operate, astronomers know exactly how much light certain types of stars put out. And if you know exactly how bright a star is, and you know how bright it appears here on Earth, that allows you to deduce the distance from us to that star. This lets us set the scale of the universe all the way out to distant galaxies billions of light years away. The real gold mine, though, is what color is the light coming to us from a different star. Quantum mechanics tells us that every atom in the periodic table absorbs and emits a unique pattern of specific frequencies. This means that by looking at the color of light reaching us from a distant object, we can determine exactly what that object is made of. Even more, we can determine how that object is moving thanks to the Doppler effect. This is an effect that produces a shift in the frequency of waves coming to us from a moving source. It's responsible for the characteristic meow noise that every kid knows a fast-moving car makes as it goes past you. As a car comes toward us, it catches up to the sound waves that it's already emitted, shifting them toward a higher frequency and a higher pitch. As the car recedes from us, it runs away from the sound waves it's already emitted, leading to a lower frequency and a lower pitch. That change in pitch as it passes, moving from coming toward us to going away, is the result of the Doppler effect. The same thing happens with light. A galaxy that's coming toward us has its light shifted slightly toward the blue end of the spectrum. A galaxy that's moving away from us has its light shifted slightly to the red. The Doppler effect is how we know that the universe is expanding and led to the idea of the Big Bang theory. The Doppler effect is also one of the keys to dark matter. Some of the best and earliest evidence we have for the existence of dark matter comes from using the Doppler shift to study the motion of galaxies, and was first collected by the astronomer Vera Rubin, who has spent more than 60 years using the Doppler effect to study how galaxies move. Vera Rubin started in the 1950s as a graduate student looking at the motion of whole galaxies and groups of galaxies. But in the mid-1960s, she started looking at motion within galaxies. A spiral galaxy that's rotating will have one side coming toward us, and its light will appear slightly more blue than it otherwise would. The other side of the galaxy will be moving away from us and will appear slightly more red than it would otherwise. The difference between those two tells you how fast the stars are going around. This is a very tricky measurement to do because the light from a galaxy is very faint. But one of Rubin's colleagues, the astronomer Kent Ford, had invented a new technique that greatly sped up these measurements. So Rubin and Ford started looking at the light coming from galaxies to determine how they're rotating. And what they found was shocking. They saw the pattern they expected, with light shifted to the blue on one side and to the red on the other side. So part of the galaxy is rotating toward us, part of it away. But as they moved out from the center, the velocity went up and remained high all the way out as far as there are stars to see. All the way out to the edge of the visible galaxy, they saw stars moving very rapidly in their orbits. This is a shocking result because everyone expected that galaxies would operate like the solar system. If you look at the planets in our solar system, the inner planets go around the sun very rapidly, while the outer planets take a much longer time to complete their orbits. This is because of the laws of physics. The force of gravity gets weaker as you go farther out, and by the time you reach the outer planets, the force of gravity from the sun is simply too weak to hold a fast-moving planet in a large orbit. Everyone expected that the same thing should happen with galaxies. By the time you reach the outer edge of a galaxy, the gravitational force of the stars toward the center should be too weak to hold a star in a fast-moving orbit, and the velocity should decrease. But that's not what Rubin and Ford saw. They saw the velocity go up and remain high as far out as there's light to see. When Vera Rubin first reported these results, everyone assumed that she must have made a mistake. So they did it again, measured another galaxy and saw the same thing, and again and again. Other people measured other galaxies and saw exactly the same thing. Every galaxy we look at shows the same pattern. The velocity of orbiting stars remains high as far out as we can detect light. The only way this can be true is if something else is providing a force to hold those stars in a fast-moving orbit. There has to be some other matter there that we don't see, 5 times as much of it as the visible matter that we do see. Over the years, lots of other evidence has accumulated that also points toward dark matter. These days, astronomers are extremely confident that for every bit of light-emitting matter that they detect, there's 5 times as much dark matter out there. We can't see the dark matter directly because it doesn't emit light, but its gravity leaves an imprint on the light that we do see. I tell this story not just because dark matter is weird and cool, which it is, but because it says something important about the nature of science. Modern science is full of things like dark matter that seem so bizarre that scientists must be making them up just to mess with your head. They seem sort of magical. But science isn't magic. Science is the result of a process of reasoning. You look at the world around you. You think about why it might work that way. You test your theory with further experiments and observations, and once you've determined what happens, you tell everyone you know the results of your tests. This is a process that we all use all the time. It's a process as old as humanity itself. It's the process you use if you decide to relax by playing a few hands of bridge. You look at the cards you have and the bids made by the other players. You think about what that tells you about what they're holding. You test your theory by playing out the hand, and if you win, you brag about it to all your card-playing friends. This process allows us to deduce the existence of things that we can't see directly. Right? It may seem magical the first time you hear about dark matter, but the process by which it was discovered is no more magical than the process of figuring out who's holding the ace of spades.